Okay, let's continue. Now it is General Chemistry Part 24. We're in the middle of introduce a acid-base reaction, which we use sulfuric acid and potassium hydroxide. Now both are strong. One is a strong acid, one is a strong base. Now there's a dispute about sulfuric acid is strong acid or not, but it's a very ionic sulfuric acid, nitric acid, hydrochloric acid are the three most commonly used strong acid in any chemistry lab. It doesn't matter you're teaching or you do research. Alright, so but of course, there's a reason people say sulfuric acid is not strong acid. Well, you can try it on your skin for 10 minutes, see what happens to your skin. But here, their reason was this. Because sulfuric acid has two hydrogen in the formula. And then these two hydrogen atoms will not be dissociated at the same time. The first one will dissociate out of the sulfuric acid formula 100% complete. But the second one take a little longer. It will only release about 1%, about 0.01 mole of hydrogen atoms for the second one come out of the hydrogen sulfate, which is HSO4 minus 1, right? But that is the dissociation process. That's what I'm trying to emphasize here. In the future, you will run into a chapter in Chemistry 142 called Acid and the Base. When you introduce acid and the base, then you will run into this kind of problem. And this is conceptually misleading if you do not consider this acid is a strong acid. Alright? Now the situation are different here. When they were talking about the second hydrogen atom dissociate from the hydrogen sulfate, which is HSO4 1 minus, alright, is the dissociation process of the hydrogen sulfate in the aqueous solution by itself. But here is not. Here is different. Because why? Because we are reacting sulfuric acid. It doesn't matter first hydrogen atom or second. With another base, a strong base. There's a constant demand of neutralization driving force. Drive these two become neutralized, and then the driving force to form what? Form the liquid water as one of the typical products of neutralization, or we call acid-base reaction. That's the difference here. Alright? So in presence of the strong base, both hydrogen atoms from the sulfuric acid will be 100% totally, completely dissociated and reacted with the potassium hydroxide. That's a total difference. So, if you don't understand this, then you need to review your general chemistry knowledge back to your middle school or high school, even university days, right? You missed it. But here's the difference. I'll try to point out. So even as a professor, full professor, and make such a fuss, says, oh, this is a weak acid. No, how can you say sulfuric acid is a weak acid? That's a joke, all right? That's funny. So that is not right. So let's talk about this reaction. In this reaction, actually they completely react with each other according to the equivalency of the quantity of number of moles of each, right? And when the reaction completely stopped, if they both completely consumed, become the salt, which we call ionic compound, sometimes people call salt. Salt is a more general layman term, but you call ionic compound is a more chemical scientific terminology. We call ionic compound potassium sulfate, right? And the water. Both were neutral, but here is not neutral. Here is very acidic, here is very basic, and this pH is going to be lower than 1, and this pH is going to be what? That's lower than 2 at least. And this is going to be much greater than 12 or 13 on the pH value scale, right? So what happened? They are completely react with each other. and then they exchange. Now we talk about this is a part of the double displacement reaction, right? Belong to that category, and it can also be classified as acid-base or neutralization reaction, right? But I also can classify as what? As water formation or liquid formation. See, so 3 categories talking about the same type of reactions. But you have to know the classification, based on what kind of concept you apply to name the type, right? So here we talk about this acid-base neutralization reaction, or driving force is forming the water and is a water or liquid formation reaction, as well as is fitting into the scheme of double displacement or double replacement reaction, right? So let's look at this. Now, couple of questions. Number 1, we always talk about if any type of chemical reaction is redox, right? In other words, involve electron transfer. Now look at, we always check for finding out that by using the knowledge of what? Oxidation state change. If the oxidation state for each element before and after the reaction as reactants and products different, then you involve electron transfer. Otherwise, would be no electron transfer, it is not considered redox. Right? It's a regular outer type, right? So here, hydrogen +1, 2 of them. Sulfate, if you learned in the past, you already have knowledge now, you know sulfate 2- is an anion, 2-, right? If the 2- matching the 2+, that be neutral, and then that is charge or the oxidation state for hydrogen and the sulfate. And we also mentioned in the past, the last part, we talk about those polyatomic anions, sulfate, nitrate, phosphate, right? Sulfite, right? Nitrite, all those chlorite, perchlorate, right? All these are polyatomic anions. They are stuck together. They never dissociate further into individual atoms of different elements. So they will be kept the same. If they don't split, should be the beginning as reactants or end up with products the same. So SO4, SO4, they don't change. And the potassium right here, check this metal. What is that family? Alkali metal, right? Potassium is always +1. You got +1 and the hydroxide is -1, so they are matching, neutralized, right? Become neutrality is a neutral compound, right? But it's not binary. It's more than 1, more than 2. Here, right? Also is a +1. Got 2 of them, so 2+ and the 2-. That's how they reach neutrality, right, for the compound. And the water, we all know hydrogen in the water is +1 and oxygen is -1. Or -2, right? Oxygen is -2. So they don't seem to have any oxidation state change. This is not a redox. Is that clear? So, but when we talk about the total number of atoms, this chemical reaction equation, it doesn't seem to be mass balance. Why? Because we have 1 potassium here, we got 2 potassium there. So we have to what? In my tips of balance equation, which says if the chemical substance involved in the reaction has or both have metal in there, we balance the metal first. So which one is metal here? Only this one is metal, right? Hydrogen is considered as alkaline, right? Alkaline metal family, the first one on top, right? But these 2, so we consider that's pure metal. We balance the metal first. If here's 2, here's only 1. So what do? So we have to what? We have to. What happened to this? I don't know what happens. All right, we have to double here, right? Double here, and then potassium balance. Now, sulfate, right? Sulfate, and the hydrogen. You see like 2 hydrogen, 2 hydrogen. No, here's a 4 because there's another 2. So total of 4 hydrogen after you balance the metal potassium, the hydrogen out of balance. Here there are 4, here are only 2. So we should also double this. When you double that, we got 4 hydrogen atoms, right? Now we have how many oxygen? We got 2 oxygen, right? 2 oxygen, 1 sulfate, 1 sulfate. It is balanced, massive balance, right? Now since it is not a redox, we cannot use electron or the charge to balance the charge unless we get into ionic equation. Now we don't get in there until later, right? This is it. So that is another example for strong acid, strong base reaction, and the neutralization reaction. The final solution is what? It's a salt, ionic salt, and plus what? Liquid water. Liquid water. So it's air right there, right? It's not gas because it's a normal temperature. It's not heat up very high, right? So that is the case. Physical state all correct. Aqueous, 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 liquid. Now that is quite important. Now you take my exam. Those small, minute difference in physical state or balance equation for the subscript of a compound formula and the coefficient for number of moles in front of each reactants products after you balance the chemical reaction, all these little things, right, make the whole chemical reaction equation valid, correct, right? We are very picky on that. That's called science. Otherwise, why is it not science? All right, so we done that. Now that's what? That's number 6, right? Number 7. That's a number 6 type. Number 7, right? Number 7. Is it number 6 or number 7? I forgot. Anyway, so let's say number 7. All right, number 7, precipitation. Precipitation reaction, right? But simply the shorthand as PPT reaction. Now, what is the definition for precipitation reaction? Precipitation reaction is the kind of reaction, right? One of the products of the reaction must be what? Must be solid. That's it, so simple, right? It's a chemical reaction right? Which must produce at least, most times is one, at least one product as solid, which means will precipitate out of the solution. At the beaker of the reaction chamber, right? That is the definition. So either way you say the reaction will produce at least one of the products will be solid, or you say that the same thing, right? So, but in order to find what kind of a reaction will produce solid products, and we must get into some kind of concept involving how to predict products from any reactants and through any type of a chemical reaction. Now we already, in that case, we already did in so far we already did a couple of things we mentioned a couple of times. All right, for what kind of chemical reaction will have what typical type of products, right? We talked about this. For instance, let's give you a review, right? Give you a review. And a single displacement, right? Normally it will form a gas, evolved out of the solution, or replace a single element as metal and then precipitate it as a solid metal as products, right? And then that's number one. Number two, and the combustion reaction always must have is what? The products as one of the two of them, right? One is going to be carbon dioxide, The other one, what is going to be? Must be water vapor, right? Water vapor. And if you have, then you have acid-base neutralization reaction. What's the typical products of that kind of reaction? The salt, or we do not use salt, we use ionic compound, right? It's a strong electrolytes and then dissociating the water solvent, form an aqueous solution, that's right here. And then another one is going to be also typical for acid-base reaction is the liquid water will be generated, right? So here is typically generate a solid, right? Solid compound. So the compound must be insoluble in the aqueous solution to be considered solid. Now, in order to understand what kind of compound will be, right, insoluble in aqueous solution, we have to introduce a table. It's called solubility of ionic compounds in aqueous solution. Now, sometimes you see a table says solubility rules of salt or inorganic salt. That's okay, but I think that's much better because we are going to talk about a salt. Also, we use layman term salt and chemical term is ionic compounds, right? And then solubility means if it's dissolving aqueous solution and then dissociate or not. If it's only dissolved, not dissociate, the solubility is zero because you have to understand the solubility here means that ionic compound dissolve into aqueous solution, water-based aqueous solvent, right, will be ripped apart by the polar molecule. We talked about this last couple parts, right? We talked about in part 21, 22. That's why we spend so much time on it. You have an ionic compound, right? Polyatomic, 1 and 2, 3, more than 3 elements involved. For instance, potassium sulfate are 3 elements, right? Potassium, sulfur, and oxygen. And then they go into water. It's by itself in the outside of being a crystal, solid. But it started dropping to the water, right? The polar molecule start working on it. Zillings of polar molecule. One end is slightly positive, the other end is slightly negative, right? So either end is going to attract to the cation or an anion or vice versa, correct? And they start to start a tug war and pulling the all pull on this cation anion out of its crystalline structure as solid, and they just rip them apart, become a cation anion pair, right? That's what we talk about. That's an ionic compound. Now solubility means they are able to, right, dissolve and dissociate. Means from the previous discussion, they were ripped off by the polar molecule water as a solvent, right? So and they become cation anion pair. Now, what kind of compound? What kind of components will be completely soluble? Now, this table will give you most of all, almost all, right? It's a table, look like small, not big table, not like a handbook, but it will confuse a lot of students at entry level for learning general chemistry, because this table is like a double-edged sword, as the common normal case plus exceptions. These are doing this, but except those. You follow me? And most of them are doing this, but a few of them not. That is what you have to keep in mind. Now, this table will be allowed to use in this level of chemistry chemistry class examinations, right? But after you did a couple times, right? Not a couple times, maybe half a dozen times, and then you may have to retake the chemistry a couple of times, and then you go, oh, this is all in my head. You remember it a bit easier. It's not too much, but at the beginning you're confused, right? You're confused. So let's talk about this. So this table have a title as a solubility of iron compound, right? Solubility of iron compound. And then in aqueous solution, why we talk about water solvents, right? So there's two groups. One's A and one's B. A is talking about compounds will be soluble. Now, what kind of compound will be soluble in aqueous solution? With what kind of components? Number one, the first family, all those alkali metal form any compound will be soluble in water. All right? No exception. There's a zero. No exception. Let's just mark it out. No exception. No exception. You see that? And here it does have exception, right? And but here, right? Here doesn't have exception. No exception. You see that? That's how it's much clearer, right? And then there's acetate, right? There's no exceptions. All right. So ammonium, NH4, 1 plus cation, polyatomic cation, right? And it will form soluble with anything else, right? That's what. No exception. Now we number 3, number 7A was a halogen, right? Halogen elements. Chlorine, fluorine, chlorine, bromine, bromine, and iodine, right? And then those were that's iodine, right? Bromide, chloride, right? Right? Those were anions. They are forming any compounds, always soluble, except forming compound with silver, mercury. Why mercury? Because it's not mercury. It's mercury. 2 mercury atoms combined in a small cluster. Each one possesses 1 plus charge, cation charge. 2 combine into 1 like a conjoined twin. You follow me? The conjoined twin, the head touch each other, right, whole body, and then it both present to the outside world as 2 plus. But they got 2 hearts, 2 livers. That's 2 heads. That's what happened here. And then it's not like a mercury itself. Now the lead, right? Lead, 2 plus. With these 3 metals, halogen will form what? Insoluble. Exception means if this is soluble, with those will be insoluble, the opposite. All right. And then the nitrate, NO3, and the chlorate, right? And the perchlorate, right? And the acetate. Now those 4 groups of components for making any other compounds with any other element, it will all completely soluble. There is no exception. You see that? The last one for soluble compounds is sulfate. The sulfate with anything will be soluble except 3, right? These 3, right? These 3, and will form insoluble salt, right? Insoluble salt. Now this is the first group A. Then the second group, we talk about compounds are insoluble with what? And have exceptions. Now what is that? The first, there's 3 categories. That's 5 categories. Now the first one is carbonate. I think we already talked about carbonate. calcium carbonate. Last part we use that example. 2 minus, right? Anion. Phosphate and the 3 minus. PO4 3 minus, right? Oxalates, that's a T right here. And the C2O4 2 minus, that's organic, right? And then here is chromates. Chromates is chrome based. The CrO4 2 minus. What's the oxidation state for chromine? +6. +6 -8 -8. Well, -8. So total outside is -2 minus, right? And those were all insoluble with anything else except with ammonium or first family alkali metals. Why? Alkali metal, ammonium, with anything, no exception, will be all soluble, even including all these 5. You see my point? So that's all correlated, right? They are related backwards, right? If they are all soluble, gotta be the exception for insoluble. You see that? All right. And second is sulfide. Now sulfide is S, sulfur with 2 more electrons, right? With 2 more electrons, just like the oxygen. Now what has happened? Well, what is the oxygen and sulfur? Oxygen is on top, sulfur at the bottom, right? They have the same family, right? Oxygen desperately need 2 more electrons to be what? Neon configuration, correct? Right? Right? And then the sulfur definitely want 2 more electrons become electronically become a argon configuration, right? 18. So gain 2 more electrons, sulfur become sulfide anion, and sulfide with anything else, anything would be insoluble except what? Except the ammonium, well, all soluble. 1A alkaline metal and the 2A alkaline earth metal they were not insoluble, they will be soluble. Now, except these two, alkaline earth, right? These three, right? So then the last one is hydroxide. The hydroxide, OH, 1 minus, anything combined with hydroxide will be insoluble, become solid, precipitate, right? Those are all precipitates except those, right? They are not precipitate except these, right? That's how you understand table. And then, of course, this time for hydroxide also has exceptions, right? Except with what? With first A alkaline metal or second A alkaline earth metal, these two groups will be still soluble for hydroxide, right? Because at least we understand 1A alkaline metal with anything else, no exception, will all soluble. So become if it's all soluble, become the exception for insoluble. Do you see my point? Insoluble, exception, all soluble, right? So that's all. Now we are going to use this table. Currently we are very handy. We are able to use this right there to make some decision what kind of compound as products out of the precipitation reaction, which one will be solid, precipitate out, which one is not going to be precipitated as solid, will stay in the aqueous solution as a free, right, cation and anion pairs, right? And then in most cases, those we will call them spectators because they are not joining the real reaction process, become the real cation and anion, which combine to each other become a solid product. We can literally filtrate it and evaporate the water, right? Get those solid products in your hand and look at them. That's the products of the reaction. Otherwise, we call what? We call chemical change process, dissociation, not a reaction. Do you see that? So let me see the time's up or not. And I got 2 minutes. My clock's, oh yeah, it's probably close enough. Okay. All right. So let's pick up one example, right? In general, right? In general format, right? So it's going to be what? It's going to be A, B, right? It's going to be aqueous. First, you start from aqueous, but both reactants must be what? Soluble. And then react with C, D, also aqueous, right? Then one-way direction. Become what? A, D, C, B, right? A, D, let's say AD is solid, goes down, plus CB, still aqueous. That's going to be the cation anion pair. This is going to be cation C, anion B, and then wandering in the vast ocean of water molecules as solvent, as aqueous solution, right? And then they never form any compound, but then they are canceled. So this kind of reaction we call precipitation. PPT right here. This is solid precipitation, right? Now, if you don't understand this, I said you close your eye, right? And imagine, oh, there's a beaker, right? There's a A, B, and the C. You drop in there. They dissociate. They're ionic compound. They dissociate. A cation, B anion, and the C cation, D anion. They wander around, and then there's a driving force. Say, okay, let's regroup, and then the A and the D, you are able to form solid. So they become solid, stuck into each other, become insoluble salt, right? Insoluble, and then they're heavy because salts are heavy. So they descend to the bottom of the beaker. That's the beaker right here, right? The beaker right here, and the solution on top, and then go down the bottom. They are literally separated, right, from the majority of other components in the solution, right? They are in the bottom. So now the reaction stopped. And what is inside the solution? The C and the B. C is cation, B is anion, they still running around, but there's no more reaction because they don't form any products. Is that clear? I think time's up. Only a couple of seconds left over. So if we want to, we can write an ion equation, right? So let's say ionic equation of this. Let's continue next section. and we're going to talk about how